Alrighty. Welcome everyone to the final day, our third day, of the Observing and Modeling Climate Variability in the Intra-Americas Seas and Impacts on the Continental Americas and the Caribbean, our virtual workshop. This is Kristen Uhlenbrock from the U.S. Climate Project Office. I'd like to go over a couple housekeeping items before we get started. These are very similar to what you've heard in the previous couple of days. First, if you have any technical difficulties, please call ReadyTalk. The number is listed here on the screen, or you can chat with a representative online on their website as well. We have our final two oral sessions today. The first one is from now until 2:30. It is session 5, and then we'll break for 1 hour for our third and final poster session, and then come back at 3:30 p.m. This is all in Eastern Daylight Standard Time for our final session and panel discussion. We'll get wrapped up promptly at 5 p.m. today. If you go to uscliver.org, you can see a link to the workshop agenda as well as the posters located there. During the poster session from 2:30 to 3:30, we do encourage you to view today's posters and ask questions and post comments for the authors to respond to. The presenters will be online during this hour and actively engaging with your questions. We will be recording this workshop, and we'll make an archived version available online shortly after everything is over next week. Everyone is currently also on mute and will remain on mute during the presentation. Each presenter will have about 15 minutes along with 5 minutes for Q&A. During the Q&A, there's 2 ways for you to ask questions. One is to type in your question in the chat feature. You'll see that in the upper left-hand corner of your screen. We will be monitoring these questions and queuing them up for the speakers as they come in. The second way to ask a question is to raise your hand by clicking on the button in the middle of the screen. This is only available if you have connected your audio over the phone or through like a headset using voice over IP. If you're just listening in, kind of broadcasting so to speak, then the best way to ask your questions is to type them in the chat and to not raise your hand because we can't take you off mute. During Q&A, we're going to alternate back and forth between the chat questions and the raised hands questions, and hopefully try to get all of them answered. When you raise your hand, we'll take you off mute and let you know you're off mute so you can ask your question. And as a reminder, please keep your questions succinct and to the point so we can be very sensitive to the 5 minutes that we have. We'll move on from speaker to speaker after each one is done. And if you did not get a question that was asked, please go ahead and type those in the chat box for us. We're going to collect all of those questions and send them to the speakers for them to answer when the workshop is over, and we'll pass those around to all the participants. I would now like to introduce Vasu Misra. He's from Florida State University. He is chairing session 5 as well as session 6. Vasu, you're up.
Good afternoon, everyone. This is Vasu Misra from Florida State University. I have the pleasure of introducing 4 speakers for this session. The first speaker is going to be Professor Eric Maloney from Colorado State University, talking about the intraseasonal variability in the IAS and its representation in models, followed by Juan Pablo Sierra, who will be talking about the Western Columbia low-level jet and its simulation by CMEC-5 models. That talk will be followed by myself. I'll be talking on the sensitivity of regional coupled ocean atmosphere simulations over the Intra-Americas seas to the prescribed bathymetry. And finally, the final talk of the session will be by Dian Putrasahan, the importance of ocean mesoscale variability of ASC interactions and heat anomaly distribution in the Gulf of Mexico. So Eric, all is yours.
Okay, can you hear me?
Yes.
Okay, great. Okay, so the purpose of this talk is going to be a few-fold. First, I'm going to give an overview of the nature of intraseasonal variability in the inter-American seas, primarily in 40 to 50-day timescales. We've heard a bit about this already this week, but it doesn't hurt to reiterate a few things. I'll try to give some insight into the dynamics of the intraseasonal variability in this region before moving on to the ability of models to simulate variability in the East Pacific and Gulf and Caribbean. And I should mention that this work is the result of collaborations with many people who I can't name all in person right here. So you'll see some of the names as we go along. Okay, so the Intra-American Seas region is characterized by extremely prominent intraseasonal variability. And so if you look at power spectra of things like precipitation, which I show on the top here, and SSTs, which I show on the bottom, you can see a significant 40 to 50 day spectral peak, not only in this field but in many other fields. And in fact, if you look at the signal-to-noise ratio of the spectral peak, is actually higher than you see in many instances in the Eastern Hemisphere. So extremely strong intraseasonal variability. If you look at a map of the basic nature of intraseasonal variations in winds and precipitation and latent heat flux, you get something that looks like the following. And so the left-hand panel here shows anomalous precipitation and surface winds during two opposite phases of the intraseasonal oscillation in this region. You have an easterly phase, which is characterized by suppressed precipitation over the eastern Pacific warm pool and surrounding areas. And interestingly, opposite sign precipitation anomalies off towards the west. And then you have a westerly phase characterized by anomalous westerly flow at the surface and enhanced precipitation across much of the East Pacific and surrounding regions. These two snapshots here hide to some extent some of the very rich nature of this variability. In fact, if you looked at the intervening phases, you would actually see northward propagation of anomalies, much like Jinan Zhang has shown in previous papers over the last 5 years. Now, if you look at surface latent heat flux, you also see something very interesting. You see that during the easterly phase, there tends to be suppressed latent heat flux over the eastern Pacific warm pool with opposite anomalies off towards the west, with just the opposite sign during the westerly phase. And this is important for reasons I'll get to later. There's some modeling studies, at least, that argue for an important wind evaporation feedback for supporting intraseasonal variability in this region, like I'll show later. Okay, so why is variability in this region important? There's a multitude of reasons, including precipitation variability over land in Central America and Mexico. But one thing that people have looked at in the past in some detail is intraseasonal variability in tropical cyclone activity. Before I mention this, I want to briefly mention that many of the composites that I'm showing here are similar if you composite based on the global Madden-Julian oscillation or a local index of intraseasonal variability. So very similar looking composites, and I'll get into later whether or not there's a strong codependence between the MJO and intraseasonal variability, or if intraseasonal variability in this region could be quasi-independent of the MJO. So I'll get to that issue in a little bit, but many of the composites I'm going to show here use, at least for now, the MJO and intraseasonal oscillation in this region somewhat interchangeably. So anyways, if you look at the left panels, you see that intraseasonal variability in this region is associated with a very strong variation in tropical cyclone activity in the Caribbean and Gulf of Mexico. This is something I documented in a paper with Dennis Hartman in 2000, where you see about a 4-fold increase in tropical cyclone genesis during the westerly phase, during the easterly phase. And there's been some more recent work recently, for example, by Crosby and Sarah, 2014, showing a very strong fluctuation in East Pacific cyclogenesis as a function of MJO phase. And in this case, there's about a 3-fold increase in cyclogenesis rate per week in phase 8 versus phase 6 of the MJO. And this is also consistent with some previous work that had been done early in the 2000s. You could actually exploit this tropical cyclone signal to predict tropical cyclogenesis if you have knowledge of the MJO some time in advance, 2 to 3 weeks. And we actually did this in a paper with one of my graduate students, Stephanie Stephanie Slade, where we developed a statistical prediction model based on knowledge of the MJO and other predictors that showed skill at predicting Atlantic and East Pacific cyclogenesis 3 weeks in advance. And so we can actually exploit these things to produce prediction capability for tropical cyclones. Okay, and one question is, why is tropical cyclogenesis modulated as a function of ISO phase? You could look at things like shear, tropospheric moisture, lower tropospheric relative vorticity, and all of these things have signals that are in such a way that you can explain the tropical cyclone modulation. But another thing that may be important for explaining this modulation of tropical cyclones is that during ISO or MJO events, you actually see a very strong fluctuation in precursor disturbance activity, in particular easterly wave activity, over the eastern Pacific. And so this is a plot from Crosby and Serra again, showing that easterly wave-filtered OLR and 700 hectopascal eddy kinetic energy shows very strong fluctuations between the MJO westerly phase and the MJO easterly phase. So one possibility for the cyclone modulation is that you have much weaker precursors during the easterly phase and westerly phase that leads to a suppression of cyclogenesis then. So that's just one hypothesis. Okay, so I mentioned before that there's a relatively prominent latent heat flux anomaly signal associated with the MJO in the East Pacific. And so there's been some work that's been done digging into the dynamics of the MJO in both observations and models to try to determine whether or not this latent heat flux anomaly is actually important for the dynamics of the intraseasonal mode in this region. I'll mention more on models later, but some models can produce a reasonable semblance of intraseasonal variability in this region. So one example is this version of the NCAR community atmosphere model that I've used in the past that produces a realistic spectral peak in precipitation and other variables at 40 to 50 days. And we're actually comparing this control experiment here to an experiment, a sensitivity experiment, where we removed variability in intraseasonal surface fluxes by setting the surface flux field to its climatological value. So this removes surface flux feedbacks in the model, and we wanted to assess the impact that this has on East Pacific intraseasonal variability. And in this case, you could see there's a dramatic decrease in intraseasonal variability in the East Pacific when you cut off this flux feedback. And in fact, the spectrum just basically looks like red noise after you do that. So it highlights a potentially important feedback due to wind-induced fluxes to the ISO in this region. Okay, so I mentioned before the question of whether or not the Eastern Pacific intraseasonal mode that we see here exists independently of the MJO, or if it's fundamentally related to the MJO forcing the East Pacific. And so there's actually conflicting evidence for this. And so a paper that one of my students led used two different models. And so one model is this version of the NCAR model, which I showed before, which produces a reasonable simulation of the East Pacific MJO, including a strong spectral peak and also realistic phase relationship between westerly anomalies and enhanced precipitation in this region. So that's a global model. And another model we used is a regional model called IRAM, which is used by people at the University of Hawaii and other places. So both of these in their control versions produce reasonable intraseasonal variability in this region. And so we wanted to see what happens in both of these models if we isolate local East Pacific intraseasonal variability from from the West Pacific. So we did that a couple of different ways in both of these models. For the NCAR model, we actually put a sponge region in the Central Pacific that isolated the Eastern Pacific from the Western Pacific by damping out any dynamical signals that would propagate eastward out of the Western Pacific warm pool. And in this IRAM model, we actually were able to more directly filter the boundary conditions of the model to remove intraseasonal variations coming into the domain from outside of the domain. And so with these two models, we actually got very, very different answers and conflicting evidence on the relationship of the MJO to Eastern Pacific variability. So with IRAM, when we filtered out the MJO from the boundaries, intraseasonal variability pretty much completely collapsed. But in this global model, we actually were still able to produce a local 40 to 50 day oscillation that looks like what we see in observations, with the isolation from the Western Pacific. And so it seems in this model that we can sustain a local intraseasonal mode. But what seems to happen in this model is if you allow communication between the Western Pacific and Eastern Pacific, it seems like the MJO phase locks to intraseasonal variability in the eastern part of the basin. So it seems like the MJO could be pacing intraseasonal variability in the East Pacific, although it may not be absolutely essential for its existence. So that was sort of a conflicting bit of evidence based on these two different models. And so I think this is still an open question that deserves a bit more research in other modeling studies. Okay, so I think I'm starting to run out of time a bit here, but this was shown by Nina a couple of days ago. There's actually a very wide variety of CMIP-5 model performance and climate model performance in general in simulating the leading 40 to 50 day mode in this region. So you could look at amplitude of the mode, you could look at the pattern correlation of the local mode in the model with observations. Either measure indicates that you get some models like these models here, which produce a reasonable semblance of intraseasonal variability, and some models which produce extremely poor intraseasonal variability in the East Pacific. So there's a very wide spread in model abilities to simulate the MJO or ISO in this region. Nina also showed that showed an analysis of predictability and prediction skill associated with the intraseasonal oscillation in this region. And a couple of the main points here is that in general, the East Pacific is characterized by lower prediction skill and predictability than the MJO, and also models are pretty far away from reaching their upper limit of predictability in this region. So there's a lot of work that needs to be done in terms of model improvement for improving the prediction capabilities of these models. And also very interesting, these models also indicate that prediction skill is higher when the MJO is active. And so this does suggest some link between the MJO and the intraseasonal mode in this model in observations, at least in the context of the MJO pacing intraseasonal variability in the East Pacific. All right, so let's move on here quickly. So we have done some research looking at the keys to successful East Pacific ISO simulation in models. And one thing that seems to be extremely important is properly simulating interactions between convection and lower free tropospheric moisture in the models. And so this is characterized by this left-hand plot here, and the y-axis here shows the amplitude of the intraseasonal mode in the model, and the x-axis here shows the relative humidity difference between the top 5% and bottom 10% of precipitation events in the model, giving some indication of convection moisture coupling. And there's a very strong relationship between amplitude and this relative humidity difference, correlation about 0.71. We've also looked at more sophisticated diagnostics like the moist static energy budget, in particular looking at a quantity called gross moist stability, which is a partial measure of the efficiency of convective moisture the ability of convection to moisture, can discharge moisture from the column. And this quantity is actually correlated at minus 0.9 to the intraseasonal mode amplitude in this region. And so this is another measure of the importance of moisture convection feedbacks for producing a realistic ISO in the East Pacific. So my last slide here is some outstanding science questions based on the research that's happened so far. So one question that's still outstanding is the degree to which intraseasonal variability in the East Pacific is independent of the MJO, so I talked about that a bit. What are the local destabilization processes for East Pacific intraseasonal variability? I talked about surface fluxes, but there's also questions about the importance of radiative feedbacks, and also fundamental questions about what sort of convective heating profile is important. One key question that has plagued intraseasonal research and is also relevant to the MJO, for example, is how can simulations and forecasts of East Pacific variability be improved without degrading other aspects of the simulation? So this is a perennial challenge that we're still struggling with. How does easterly wave variability feedback to influence the East Pacific intraseasonal oscillation? This is an interesting question. And more generally, is easterly wave formation and subsequent cyclogenesis predictable based on knowledge of the state of the MJO and its regional manifestations? I think we've done some work showing that this is true, but there's still a lot more work that needs to be done here. In particular, creating improved models that can help us to realize some of the possible prediction skill that we see in this region. And one last thing, I'm going to give a plug for this. I've been talking with several researchers interested in the East Pacific on organizing a possible tropical East Pacific convection field program called OTRIC that tentatively we're thinking about for the summer of 2018. And a field program in this region that is relatively poorly sampled might actually help to answer some of these outstanding science questions, not only related to the ISO, but tropical convection in this region in general. So that's something just to put on people's horizons. Keep an eye out for that. And with that, I think I'll stop there. Thank you very much.
Great, thanks, Eric. If anyone has questions, make sure you go ahead and type those in the chat feature or raise your hand, and I'll turn it over to Vasu.
Thank you, Eric. I will first give a chance to the audience to see if they have any questions. I guess there's one already on the chat box. That's from Chunzai. Kristen, would you take over on that?
Sure thing. Eric Chunzai wanted to know, is there any interaction between interseasonal variability and longer timescale variations in the eastern North Pacific Intra-Americas Seas regions?
Yeah. I don't think that there has been that much work done on that so far in terms of characterizing those interactions. I think it's logical that there should be. For example, if you saw fluctuations in the North Atlantic subtropical high on longer time scales, those would likely affect the basic state in the Caribbean and Eastern Pacific. And we've actually shown in past work that the basic state, in particular the low-level winds in the Eastern Pacific, is extremely important for being able to properly simulate the ISO in a model, for example. And so if you had observational fluctuations in the basic state in the East Pacific associated with fluctuations in the North Atlantic high, I suspect that there would be a very strong relationship and very strong modulating effect on the intraseasonal oscillation in that region. I also think that there should be a pretty strong effect on between ENSO and intraseasonal variability, although I don't think that the degree of that interaction has really been documented fully to the extent that it should.
Eric, this is Vasu here. You showed this interesting metric of moisture discharge from the column being an important parameter to determine whether the model does well with the intraseasonal variability. So based on that information, is it possible to say why some of the models which have the moist convective adjustment type of closure do better in terms of intraseasonal variability, but the mean climate looks not as encouraging?
Right. So, looking, I think I brought this plot back up. So we've actually seen in some models that you can get a very, very strong MJO or ISO in the model by turning up the convective entrainment rate to extremely high values. And one effect that happens when you do this is that you make the convective heating profile in these models extremely bottom heavy, much, much more bottom heavy that you actually see in observations. And an extremely bottom heavy heating profile actually corresponds to a situation where convection is actually extremely inefficient at discharging moisture from the column, and in fact, imports moisture into the column when you do have appreciable convection. So there's errors there that are created in terms of the mean state of convection, which I think are extremely unacceptable when we're thinking about climate simulations, particularly at other time scales. What I think that we need in terms of both realistically simulating the mean state and realistically simulating the intraseasonal variability is for these models to produce a realistic mix of convective variability in modes. By that I mean it should not only be able to simulate deep convection like stratiform and deep heating modes, but the models also have to produce realistic shallower clouds like cumulus congestus. And I think it's only if the models simulate a realistic mix of clouds in that manner can they actually get both the mean state and variability right. And there was a very, very interesting paper by Minoru Chikura in 2014 that argued exactly that during the enhanced phase of the ISO, and they were actually looking at the MJO, there exists both a realistic population of congestus clouds and deep clouds in models that tend to produce a good MJO. And I think if you do that, then you're able to get the intraseasonal oscillation for the right reasons that also doesn't degrade the mean state.
All right, thank you. There's another question, but in the interest of time, let's move on to the next talk, and that question will be sent over to Eric, who can probably answer it offline.
Great, thanks. We need to test. Juan, can we test your audio before you get started?
Okay. Can you hear me?
Yes, we can hear you.
Well, can I start my presentation now?
Yes, please go ahead and get started and let me know if you have any problems navigating the slides. But you're up.
Okay. Thank you. Good afternoon, everyone. My name is Juan Pablo Sierra, and this is my work team, Joana Gudelo, and the professors Paola Arias and Sara Vieira. Our work is about how well global climate models represent the basic features of the Choco jet. We are from Colombia, from Universidad de Antioquia. This work is important because, first of all, Choco jet transports significant quantities of moisture from the Pacific Ocean into western Colombia, especially during September, October, November. But this low-level jet is not important only for the moisture that it carries, but also for its interaction with other atmospheric phenomena, such as the ITCC, the Caribbean low-level jet, and the equatorial metropospheric easterly jet, which induce the formation of mesoscale convective systems in the region. These systems contribute to around 70% of annual precipitation over western Colombia. On the other hand, proxy evidence has demonstrated that these jet was stronger during the last glaciation due to La Niña-like conditions, which turned Western Colombia wetter. This is a proof that Choco jet can suffer alterations as a consequence of climate change, what leads us to the question, what could happen with the Choco jet under a warmer climate? Therefore, the first step is to assess how well global climate models represent the present time features of this jet. These are the datasets that we use: era interim reanalysis for winds, pressure, and temperature. For precipitation, we use GPCP and TRIM. We use the eTopo 1 digital elevation model from the NOAA for the topography, and 26 coupled or CMIP models and 11 uncoupled or AMIP global climate models from CMIP 5 project. We use the historical experiment, which involves natural and anthropogenic forcings in the time domain 1979 to 2005. We use AMIP and CMIP models in order to identify whether errors come from the atmospheric or oceanic component of models. We keep models at their original resolution and use bilinear interpolation in calculating ensemble means using the Cursor model resolution. For quantifying the quality of the representation, we use the root mean square error and the spatial and time correlation coefficients. We use cluster analysis for model classification and factor analysis to visualize the goodness of the model groups. Choco jet result as an inversion of easterly winds in front of Colombian Pacific coast. Figure 1 shows the annual cycle of the jet. This jet is centered at 5 degrees north and 80 degrees west, and its core is at 925 hectopascals. This jet has a stronger activity during boreal fall. You can see that in the red circle, and minor intensity during February to March. Choco jet exhibits latitudinal amplification and deepening. First, figure 2 shows the vertical structure of the jet, zonal winds at 80 degrees west. And figure 3 shows the spatial distribution of horizontal winds at 925 hectopascals. Choco jet exhibits a latitudinal amplification and deepening through the year. These changes in the structure of the jet are not seen in other reanalyses, such as MSIP and CAR and CFSR. We can see the latitudinal amplification of the jet between March, April, and May, and September, October, and November, and the migration of the jet here in the red circles. In order to classify objectively the models, we use cluster analysis with the root mean square error and correlation coefficients of the basic features of the jet that we mentioned previously as indicators of the model quality representation. So we here can see that distance among different groups increment when we reach 3 groups, what means that the groups are significantly different from each other. Figure 4c shows the scatter plot of the 2 first factors, which explain around 80% of the variance of these indicators. We can note that the 3 groups are very well differentiated from each other. Figure 5 shows the differences in the annual cycle between each group and era interim. At the upper right corner, we can find the reference figure. What we can remark here is that the worst models present the Choco jet southern from its real position, producing this red bias during the whole year. and these models present no jet activity between March and May. BEST and AMIP models exhibit a southern Choco jet, but only between October to December. This can be seen in these black circles. The three groups present the major activity of the jet 1 month before the observed maximum during August to October. That is what we see in these green dashed circles. As in the previous slide, we can find the reference map at the upper right corner. This figure presents the vertical structure differences of groups from ERA for boreal fall, what is the period of intense activity of the jet. We can see that worse models present shallower jet, especially during September, October, and November, and stronger zonal mid-tropospheric winds the whole year. Best models have a well-represented vertical structure during boreal winter and spring, but shallower during boreal fall, and they present slightly stronger mid-tropospheric winds. Finally, AMIP models present stronger mid-tropospheric winds, especially during boreal spring and summer. The spatial distribution of horizontal winds is shown in Figure 7 at 925 hectopascals for boreal fall. Worse models present a stronger trade winds and a stronger Caribbean low-level jet during the entire year. The shift of direction of horizontal winds due to the eastern flank of the Andes is absent in these models. The winds coming from the Peruvian and Ecuadorian coast are underestimated. The Choco jet is southern from its real position. On the other hand, BEST models show a better topographic change direction, better representation of winds coming from southeastern tropical Pacific, and a better latitudinal location of the jet. AMIP models are similar to BEST models, but with their best representation during boreal winter and spring, and its worst representation in boreal summer and fall. It has been established that Choco jet is the result of some atmospheric and physical phenomena. The main are, first, differences of temperature and sea level pressure among these regions: Western Colombia, Pacific Colombian coast, and Niño 1-2. The topographic lifting of the air masses of the jet, the interaction of this jet with the mid-tropospheric low-level jet, the change of Coriolis sign once the south winds cross the equator, and the latent heat release in mesoscale convective systems over region. We assess the representation only of the two first of these phenomena. Figure 10 shows the annual cycle for differences of temperature at the right column and pressure in the left column among the regions shown previously. In general, it is easy to note that BEST and AMIP models present a better representation for Western Colombia to Niño 1-2 and Pacific Colombian coast to Niño 1-2 regions. Worse models underestimate the magnitude of the differences for both temperature and pressure for these regions. Annual peaks are 1 month in advance for the three groups, what explains that the Choco jet presents its peaks 1 month in advance too. About the representation of the topography, we use eTopo digital elevation model for calculating the root mean square error and bias over the region. We found that the BEST models present a better representation of the topography than the worst models. All groups present an underestimation of the topographic gradient in the Andes region, what means that models underestimate the height of the Andes and overestimate the height of the lands that surround them. A recent study has found that low-level circulation over the Andes is sensitive to the height of this mountain chain, and they have demonstrated that By doubling the real height of these mountains is reached a well-developed South American low-level jet. Choco jet index is defined as the zonal wind average at 80 degrees, 81 degrees west at 925 hectopascals and between 5 degrees south and 7 degrees north. We can see that the jet peak occurs during September for all models, and we must remember that the jet turns erroneously southward during October, November, and December. For the precipitation over western part of Colombia, we can see that BEST and AMIP models present a better representation of the precipitation cycle, especially during September, October, November, and December. However, all models present an underestimation of the rainfall in these months, which seems to be related with the migration southward of the jet during these months. As a conclusion, we want to highlight the following. All models present the existence of the Choco jet during almost the entire year, except WORDS models which present no jet activity during boreal spring. Maximum intensity of the jet is 1 to 2 months earlier in all models, and this error comes from the atmospheric component. WORDS models tend to keep the jet further south during the whole year. This seems to be related with a misrepresentation of the interhemispherical temperature and pressure differences. All models present a southward migration of the jet during September, October, November, and December, error that is originated in the atmospheric component. There is a general underestimation of the jet curve velocities during most of the year for all models. There is a misrepresentation of the temperature and sea level pressure annual cycle differences between Western Colombia and Colombian Pacific coast regions, even for AMIP models. Topography representation can lead to a better representation of the jet, and finally, a better representation of the jet can improve the precipitation simulated over certain regions of Colombia, such as western part. Thank you very much.
Thank you very much. Are there any questions for Pablo Sierra?
Vasu, looks like we have one from German.
Please go ahead.
Yes. He writes, why did you select the ERA1 reanalysis as your control for your reference model?
Yes, we found in many references that this reanalysis has been highlighted as one of the most or the best reanalysis to represent surface winds and precipitation in North and South America, precipitation in Amazonia specifically. But we also analyze other reanalysis such as CFSR, that is the last generation of the NCIP and CAT reanalysis.
And I think this is wanting to elaborate on that. Can you expand on the differences between CFSR and ERA1?
Yes. One of the differences in the representation of the jet is the amplitude and latitudinal migration of the jet that I mentioned before. In the CFSR reanalysis, it is not present, but in interim reanalysis, you can see the migration and latitudinal amplification of the jet.
And I think Germain also wanted to add a comment that there's a poster in the Wednesday session 1 by Yepes et al. That details a 2-year field campaign to measure the Choco low-level jet off the Pacific coast of Colombia. So maybe if you or others who are interested want to check out that poster, he's pointed that out. Vasu, looks like I have one more question here, and then maybe we'll go back to you. Ernesto wants to ask, aside from the horizontal winds, what is the quality of the model representation of atmospheric moisture? And he means atmospheric moisture in the regions of the Choco jet.
Okay, that is a difficult question because the moisture transport carried for this jet is a little tricky for the reanalysis. I have found in references that the moisture transport by the jet is different from each reanalysis that you use. There is no an agreement among reanalysis in the quantity of the moisture that this low-level jet carries.
Okay. Thanks, Vasu.
Yes.
Great. If you don't have any questions, I think you're up.
All right. Thank you once again, Pablo Sierra, for the nice talk. So let's move on to the next talk, which incidentally is being given by me. Okay, so I'm talking on the sensitivity of regional coupled ocean-atmosphere simulations over the Intra-Americas seas to the prescribed bathymetry in the model. And I have to acknowledge my colleague here, Dr. Akhilesh Mishra, who has helped me a great deal in producing some of the results. Before I get on to showing you the results of the simulation from this regional coupled integration, I would like to first start talking about the importance of this Atlantic warm pool, and I'm probably belaboring this point given the fact that there have been several talks as well as posters in this workshop which have claimed the importance of the Intra-American Sea on the climate variability both in the North American continent as well as in northern South America. One of the prime examples is the purported influence of the Atlantic warm pool on the Atlantic hurricane activity, which is shown on the right 2 panels over here. You can clearly see that there is quite a bit of interannual variations in the Atlantic tropical cyclone activity, which is shown as the Atlantic TC track density per 3 degree by 3 degree cell, that in large Atlantic warm pool years you have far more number of tropical cyclones and the small Atlantic warm pool. Yesterday Chunzai also showed in his talk that it has some influence on the tracks as well, which is also quite apparent in these 2 plots as well. You see more of these Gulf tropical cyclones forming in large Atlantic warm pool areas compared to the small Atlantic warm pool areas. There is also considerable interannual variability in the size of the warm pool. You can see in small AWP years, it is relatively small compared to very large Atlantic warm pool years. The top panel is the climatological Atlantic warm pool year. There are other figures in other literature which point to the fact that the hydroclimate in North America, besides the Atlantic tropical cyclone activity, seems to be modulated by the Atlantic warm pool. So if I proceed to the next slide, what we see is a very sobering picture of the area of this Atlantic warm pool defined by the 28.5 degree isotherm by the various CMIP-5 models. The first row over here is the ER SST V3, the Reynolds SST version 3. The area is in million square kilometers. And you can see at its peak in August, the area occupied by 28.5 degree isotherm in the Atlantic is about 3.7 million square kilometers. And if you look through about 80 different CMIP-5 models, none of these models are reaching anywhere close to even 50% of or 60% of the observed seasonal peak in the area of the Atlantic warm pool, except for two models. One is the GIST model, and the other is the CSIRO model, which do reasonably well, but still do have significant other biases in other tropical oceans. Especially, it has a very warm bias across tropical Atlantic. But what I would like to get your attention to are two models, CCSM4, which at its peak has an area of about 1.31 million square kilometers as against 3.72 in the ER-SST-V3, and GFDL ESM2G, which has about 0.81 million square kilometers as opposed to 3.72 in the observation. So there's a significant cold bias in both of these models. So the attribution of this cold bias has been in many of the papers that AOML has published, seems to suggest that AC fluxes are to blame, especially the cloud radiative fluxes are quite important in the upper ocean heat budget. But in a seminal paper, in a theoretical study that Amy Clement and some of our co-authors had done, looking at the maintenance of warm pool in the tropics, and they specifically focused on the warm pool in the Western Pacific, they suggested that the ocean dynamics also plays an equally important role, and in fact is absolutely essential to maintain warm pool. So what I would like to do is bring your attention to the ocean transport, heat transport in this area. And what I would like to focus on is the meridional transport through the Yucatan Channel. So in the top panel, I'm showing you three curves. The black curve is from the soda reanalysis version 2.2.4. The red curve is from GFDL ESM2G, and the blue curve is from CCSM4. So if you look at the mean transport from CCSM4, it is about 31.72 swerdrups. And in GFDL ESM2G, the mean is about 16 swerdrups, almost half of what CCSM4 is showing. And in soda, it is right in the middle, about 24 swerdrups. If you look at the standard deviation, the soda reanalysis shows about 4.42, GFDL shows 3.09, CCSM4, which has a higher mean flow, has a much lower standard deviation, and it's quite apparent from this 20th century simulation that was part of the IPCC AR5. So there are lots of disturbing things here. First of all, both these models have a cold bias. GFDL seems to have a much larger cold bias. CCSM4 has slightly less cold bias than GFDL, but nonetheless has a significant cold bias. And despite the fact that the mean transport through the Yucatan Channel is pretty high compared to soda reanalysis or GFDL, CCSM4 continues to have a cold bias. So just imagine if the heat transport were to be right, this transport through the Yucatan Channel were to be right in CCSM4, it is more than likely that the cold bias could have been far more grave. So the simulation of the SST in the intra-American seas is certainly bolstered to some extent by this erroneous, very high mean transport. Similarly, if you look at the heat flux through the Yucatan Channel, there's a huge disparity between these two CMIP-5 models. And if you look through the literature, both these models have been widely used both to understand the 20th century simulation as well as to project the climate in the North American region as well as in North and South America. So we ran two regional climate model experiments independently for 32 years at 15 kilometer grid resolution, forced by ocean reanalysis, soda reanalysis for the oceans, V2.2.4, and atmospheric reanalysis, R2. And the RCM that we used was the regional spectral model, which is coupled to ROMS. Both have identical resolution and an identical grid, and so they exchange fluxes at intervals of 1 day. So we call one experiment as RCM1, which is run with the fine-scale bathymetry from eTopo5, and the other one is run with a coarser bathymetry, the smooth version of the above bathymetry. And just to illustrate the differences in the bathymetry are shown here. Once again, RCM1 has finer bathymetry, RCM2 has a coarser bathymetry, and you can see the differences here. The Yucatan Channel is shallower in the coarser bathymetry compared to the fine bathymetry. And there are other differences in other parts of the region of this regional domain. When you look at the SST simulation, the RCM1 warms a bit more than the RCM2. This is the June, July, August seasonal SST climatology. Nonetheless, if you compare it with observations, there are some very large errors of the order of 1.5 to 2 degrees error in both RCM1 and RCM2. So the order of correction by just changing the bathymetry, although does not rectify it significantly with respect to the observations, but it is at least pushing the RCM2 integration towards the right direction by at least warming over significant parts of Gulf of Mexico and over subtropical Atlantic Ocean. If I look at the ocean heat transport or the heat content which is shaded in color and look at the difference between RCM1 and RCM2, you do see that the heat content has increased. The heat transport through the Yucatan Channel has increased when you prescribe a finer bathymetry, and even the Gulf Stream has strengthened and the heat content along the Gulf Stream has also improved. If you look at the surface ocean currents as well, you can see, and this is the difference between RCM1 and RCM2, you can certainly see that the loop current is far more well defined in RCM1. It was very poorly defined in RCM2, and in fact, RCM1 also has some eddy shading events which RCM2 did not have at all. So there are some improvements, but certainly it has not rectified all the errors that we would have liked it to. If you look at the monthly mean volume flux through the Yucatan Channel between RCM1 and RCM2, the mean in RCM2 is about 18.37 Sverdrups, which is the coarse bathymetry. RCM1 is about 26.62 Sverdrups. Standard deviation is certainly much higher than what the SODA shows, 4.32 Sverdrups. Now, if you look at two observational studies of the transport through Yucatan Channel, one from Candela at 2003, when they examined, say, from about 2002 to 2005, I think, their mean transport through the Yucatan Channel was about 23.6 Sverdrup, and more recently, Athi et al. Published in GRL, with a mean transport of about 26.2 from about 2010 to 2013. So there is significant interannual variations, and in fact, the standard deviation is approximately about 3.2 Suvorov. If you take a cross-section across the Yucatan Channel, you can see the return flow somewhat well depicted in RCM1 compared to RCM2. This is again soda. Again, I don't want you to believe completely that soda is observations, but again, in the absence of observations for a very long period of time across this channel, soda seems to be our best bet to examine these climate simulations at the moment, given the fact that the observations display such large interannual variations. If you again look at the monthly heat flux, you again see that this is the RCM2 has about 21.13 petaflux through the Yucatan Channel. The mean in RCM1 with the fine bathymetry has about 30.62 petaflux. And soda also seems to have something comparable to what RCM1 has. But certainly, again, the standard deviation is much larger and comparable in these two compared to what the soda shows. Once again, the return flow under the surface around 1,000 to 2,000 meters, 1,000 to 1,500 meters is clearly seen in RCM1, very faint in RCM2. So this is encouraging. So in conclusion, I would like to say that the cold bias of the Atlantic warm pool in CMIP-5 models is significant. The area seems to be underestimated by over 200% in majority of the models. In fact, the couple of models which do show somewhat comparable areas of the Atlantic warm pool have some other major issues in the tropical Atlantic, and we could not use it purposefully for some of the other, to compare these two models with the rest. The two of the CMIP-5 models show very large differences in the transport through the Yucatan Channel. The one with the higher transport, that is CCSM4, displayed larger Atlantic warm pool than the GFDL ESM2G, but yet had a cold bias, and the area was still underestimated quite significantly by almost 100% or more. Even with the fact that the transport through the Yucatan Channel was almost 1.5 times more than what observations seem to indicate. The RCM experiments with different bathymetry confirm the transport through Yucatan Channel does affect the SST and heat content of the IAS. I think that is an obvious point, that you have these warm waters from the deep tropical oceans coming into the subtropical regions. But more importantly, what these experiments are showing is that even if you have a relatively high resolution, you could have a very poor simulation of the ocean dynamics in the region if you don't prescribe the bathymetry properly. So even at 15-kilometer resolution, you could have very poor transport if you don't pay attention to how bathymetry is prescribed. Now, it is not very easy to prescribe very fine resolution bathymetry because you reach into some sort of numerical instability issues, and so one has to hit a very careful balance at a given resolution of how these bathymetries and passages are prescribed in the model. The transport through the Yucatan Channel obviously can be modulated by the bathymetry because it dictates the potential vorticity through changes to depth of the water column. So after all, this is part of the western boundary current, and so it is dictated theoretically by the potential vorticity conservation. So if you are changing the bathymetry, you are changing the depth of the water column. So you obviously modulate the transport through the column. So even in a regional model where you're prescribing at the lateral boundaries this large-scale ocean reanalysis, you're not able to preserve the large-scale forcing on this transport through the Yucatan Channel simply because the depth is too shallow or the passages are not well prescribed. I have not touched upon another important area. There are passages through the Caribbean, through the Lesser Antilles and the Greater Antilles that also need to be resolved to get the density gradients right in the ocean, which is also important for the flow through the Yucatan Channel, but that's for later talk. So improving transport through Yucatan Channel will not necessarily fix all problems, but certainly would. It's a tractable problem, and I was just wondering if IPCC in its next round would use this metric through the Yucatan Channel as one way to, or one of the metrics to improve when we move on to AR6. With that, I'll stop. Thank you.
Thank you, Vasu. We do have a few questions. I think if you can see these, let's start with Eric's first. I think you were touching on this a little bit here, but we'll start with Eric. He wanted to ask, have you noticed any relationship between CMIP-5 model resolution and the ability to realistically simulate the Atlantic wormhole?
I have not personally classified these model resolutions and compared it to their AWP simulations because the 18 or 20 models that we examined were really very bad, at least by the standpoint of the metric of the area of the Atlantic worm pool. So, and moreover, we saw with these two examples, CCSM4 seems to have slightly higher resolution in the meridional direction for the ocean grid, maybe twice as high as the GFDL. But it has certainly pushed the transport way too high, and the standard deviation is extremely weak. So I don't know what the implications would be. So it's not a straightforward problem that if you increase the resolution, you would all of a sudden improve all of these quantities. I think there is far more details of the model that need to be looked into besides just jacking up the resolution.
Great. We have about 1 or 2 more minutes, so let's do at least one more question, maybe two. Ruoling asked, regarding the comparisons made at Yucatan Channel, have you also compared modeled transport values against observed Florida current transport?
That is underway at the moment. So we are just about computing the transport through the Florida Straits.
Okay, good. Let's do Yolan's question, and then we're going to have to flag the other question for later. Yolan wants to know, have you looked at the relationship between the representation of the Atlantic wormhole and rainfall patterns over Central America, such as the MSD?
In fact, we are slowly moving westward, but we see a huge impact on the peninsular Florida rainfall with the Gulf Stream. So the transport through the Yucatan Channel does impact the Gulf Stream, the strength of the Gulf Stream, and the location of the Gulf Stream with respect to the east coast of Florida. And so we see some significant impact on the warm season rainfall over peninsular Florida. There are some interesting things happening as well in Central America, but we have not had the time to look into the simulations yet over that region.
Okay, great. Thanks, Vasu. If there's any additional questions, which we do have some here, we're going to queue those up for later. Go ahead and type those in the chat box, and we'll make sure Vasu gets those answered for everyone. Thank you, Vasu. Let's move on to the final speaker, Dion.
Hi.
Hi, how are you? You
Good.
are up, and your audio sounds great, so take it away when you're ready.
All right, thank you. So good morning and good afternoon to everyone, and thank you again for staying and listening in to this last talk of the session, and also thank you to the organizers for this opportunity. I'd like to first acknowledge my collaborators, Igor Kamankovic and Ben Kurtman, and all three of us are from the University of Miami. My presentation today is based on some very recent work, so the results are preliminary, but I think they are interesting and they highlight the importance of mesoscale variability in the Gulf of Mexico. So first off, I think we are all pretty familiar with the presence of a loop current and the loop rings in the Gulf of Mexico that can drift for months and form pools of warm water, warm reservoirs that can affect tropical cyclones and hurricanes. And there's also the Intra-Americas seas, the circulation around here that's dominated by the Caribbean current, the loop current, and the Florida current. So, well, the thing about it is that these currents, the circulation, they form quite a major conduit for ocean heat transport and powerful mesoscale eddies. And yet in the system of currents are quite underrepresented in current generation global coupled models. So for instance, like the CMAP5 resolution models. So here we have the CMAP5 models. We can represent a model of similar resolution, which is 1 degree ocean resolution in the CCSM models, such as the Community Climate Systems model. You have a 1 degree ocean, and we can capture some semblance of the Caribbean current as well as the Florida current. And if you want to really, really try to convince yourself, maybe a tiny little loop current down there. But clearly, we can see that in a high resolution, so if we use a 1/10 degree resolution of the ocean, you can capture this circulation really well. And it is a robust representation, as well as not just in the mean state, but in variability. For instance, in the sea surface height, you can see quite a bit of variability along where the loop current is, so probably the advancement and retreat of the loop currents as well as the propagation of the loop rings. I have a slightly different color scale here for the sea surface height variability when we look at the low resolution run. The difference in the color scale is just to give a chance for the low resolution to show some sort of variability, but we can see that it's pretty muted. So if we take a look at the sea surface temperature variability, again in a high resolution case, in high resolution coupled run, we see quite a bit of variability close to the shores, in regions where you have shallow waters. But I think what I want to highlight is again this region where you have the loop current that is varying quite a bit, as well as the propagation of these eddies. And this vicinity here is also reflected with a positive correlation between the latent heat flux and the SSTs. So what it suggests is that we have ocean forcing on the atmosphere where you have warm SST waters that support more latent heat flux going out of the ocean. If we look at the low resolution runs, we see an opposite correlation suggesting mostly increased latent heat flux, probably due to increased evaporation that cools down the SST. So these differences between low and high resolution models, differences in the correlation is quite typical. So it begs the question then, why is it in the high resolution we can get this positive correlation for an ocean forcing, and what exactly supports this latent heat flux? And so the most intuitive process to turn to is heat advection, or equivalently in the upper ocean heat budget, we can think about it as divergence of heat. So So here we have a correlation map showing correlation between latent heat flux, and again this is SST here. And true enough, we see the support of divergence of heat in the upper 200 meters of the ocean that has a negative correlation with the heat flux going out of the ocean. And it basically supports the idea that you have a convergence of heat in the upper 200 meters, and this supports the latent heat flux going out of the ocean. Now, if we decompose this divergence of heat flux into a mean component and a sub-monthly component, and then we take the correlation between these components against latent heat flux, we can see that most of the heat flux out of the ocean seems to be supported by the sub-monthly scale of heat flux divergence. So this is, to me, at first sight, a bit counterintuitive, since the common thought is typically that a strong mean current, so in the mean you have this warm current warm waters from the Caribbean Sea that's being brought into the Gulf of Mexico, supporting the warm anomalies there and probably fueling surface fluxes. But what we see here is actually pretty counterintuitive in that it's mostly in the sub-monthly scale. So what I did first was let's take a look at the magnitude of these temperature vectors in the upper 200 meters. Here we have climatology, 54 years, so that's the length of the coupled run that we had. Took a climatology of it, and we can see that in terms of the magnitude of these temperature vectors here, you have the total, and if we decompose it into the mean and sub-monthly part of it, indeed we see that in terms of the magnitude, it's mostly in the mean, and a little bit of it in the sub-monthly scale. So, true enough, I mean, in magnitude, it's in the mean, but for the ocean heat budget, the more important term is actually the divergence of heat. And if we look at the divergence of heat in the same sense, here we decompose again to a mean part of it and the sub-monthly scale, and we can see that most of the divergence and the total divergence seems to be carried on the sub-monthly scale. So I think if we take both these slides together, they pretty much tell us that we can have these really large vectors, large heat transport in the mean current, but that the important contributor would actually be the heat divergence, and that is mostly carried in the sub-monthly months. So next I'm going to shift gears a little bit and focus more on coherent mesoscale eddies and their associated air-sea interactions. In particular, let's take a look at anticyclonic eddies in the Gulf of Mexico. Skip. There you go. Anticyclonic eddies in Gulf of Mexico. So what we did here is we identified anticyclonic eddies based on the sea level anomalies using the Cooper-Wise parameter. I picked mostly, we focused on anticyclonic eddies because typically loop currents and the loop rings, they tend to be characterized by anticyclonic vorticity anomalies. So here we identified over 1,100 anticyclonic eddies over the 54 years of our runs, and I created a composite of it, and they have an average diameter of about 350 kilometers. So when we built this composites, we normalized it to their radii, and such that we placed the origin here as the centroid of those eddies, and 1 and 2 represents one radius, 2 radius of the eddy itself. Contours are sea level anomalies, with the outer ring is 1 centimeter, the inner is 10 centimeters, 20 centimeters, 30 and 40 centimeters at the center for sea level anomalies. So here we have is a composite of the SSTs, and we see the usual meridional gradient of the SST, and a bump in the middle that is imposed by the eddy. When we just look at the SST anomalies, we see to the northwest quadrant we have the warm anomalies. We have the warm anomalies over northwest quadrant. And so I'll talk a little bit later about why it's on the northwest quadrant, but first let's look at the imprint this has on the atmosphere. And so if we co-locate those variables from the atmosphere with the anticyclonic eddies that we identified over the ocean, you can see that the latent heat flux is co-located with the warm anomalies here. So there's this idea that the SST anomalies from the ocean is forcing the atmosphere, as well as a deepening of or a higher boundary layer height in the atmosphere, same co-location. And if we look at the surface atmospheric circulation, again we see a convergence of wind right on top of the warm anomaly. So typically for mesoscale SSTs, there are two mechanisms that we think of in which mesoscale SST can force the surface atmospheric circulation, one of them being the vertical mixing mechanism that is typically explained by a co-location of the downwind SST gradients with wind stress divergence. However, this doesn't seem to be the case. There seems to be a spatial lag in that. So the other mechanism, which is the pressure adjustment mechanism, which pretty much says that we have a warm anomaly that would induce a surface low, and in that sense, a surface convergence, such as this one that we see. So a surface low basically inducing a surface convergence, and that's how you change the atmospheric circulation right above a warm anomaly. And this is what we see, and it's explained through a co-location with the Laplacian of SSTs and the wind convergence right over the warm anomaly. So in that sense, if we extrapolate that idea over a warm anomaly, we have this wind convergence. We can also take a look at the moisture convergence. And so again, this is now a composite of the moisture convergence. And again, we have a co-location on the northwest quadrant. And if we take a vertical transect across 0.5 radius, the 0.5 radius to the north, which is in this case here, this is the vertical transect, we can see that this moisture convergence is occurring in the lower levels of the atmosphere, and a signature of that bump that is seen within the boundary layer. And this is in line with the idea that you have a deeper boundary layer height right above the warm anomaly, where you have convergence of both moisture and probably winds. And along with this, what we have is a convergence could induce convection. And so what we see is that when we build a composite of precipitation or convective precipitation, we also see a increased convective precipitation right above the warm anomalies. So this is basically an idea of having mesoscale sea surface temperature features that can affect the overlying atmosphere. Now, if we return back to see what might be causing this warm anomaly on the northwest quadrant, we see we just take a look first again to the magnitude of these temperature fluxes in the upper 200 meters. And you can see we kind of have this half curve here that is probably what follows the loop current. And so you can see that you have a strong loop current. A lot of the magnitude of this heat transport seems to be carried in the mean. But again, when we look at the divergence, which is what is important in the heat budget, you can see that the convergence of heat tends to be on the northwest quadrant, and the bulk of this convergence seems to come from the sub-monthly scale. So the idea is that we have the heat convergence in the upper ocean that supports the SST that again can have an imprint on the overlying atmosphere. So in summary, pretty much what we have is a positive correlation that we see in a latent heat flux in SST that indicates an ocean forcing to the atmosphere, and we see this only in the high resolution case. And this is supported by a temperature flux divergence, mostly on a sub-monthly scale, even though the magnitude of the temperature flux is larger in the mean. And when we focus and take a look at anticyclonic eddies from loop currents and rings, there is this imprint on the atmosphere that we see on the northwest quadrant where the warm anomaly resides, coincident with more heat flux coming out, a deepening of the boundary layer, a convergence of wind and moisture, and more convective precipitation over the warm anomaly. And this warm anomaly is again seems to be supported by sub-monthly divergence of temperature flux. Thank you.
Thank you, Dion. Vasu, do you have any thoughts or questions before we go to the audience?
Sure. It's a very interesting talk that you just gave. When you say that latent heat flux, the sign of the correlation between latent heat flux and SST tells you which way is the forcing between the atmosphere and the ocean, does it also give you some idea about the forcing for rainfall from SST as well?
Well, I think that was what I was trying to find the connection, so I used composites instead. If we just look at the correlations just as on a map, it's the correlations when I made them was not as high. So you have this really high correlation between latent heat flux and SST. This seems to be pretty direct, and after all, latent heat flux is at the surface, so the correlation is really high. When it comes to precipitation itself, the correlation is much lower. I mean, we see some correlation, but it's I have to investigate a little more to see whether it's really significant. But I am pretty sure it's not going to be as high.
The reason I asked that question is because there have been several studies which claim that in a projected climate, we might, this region over the intra-American seas, may have more rainfall in a high emission scenario climate. And one of the reasons being that it is the remote forcing from the Pacific that seems to influence that kind of a signal. But if high resolution models like yours that you just examined seem to suggest that the local SSTs may play a far larger role, then maybe those results may be a function of these coarser CMIP5 models.
I see. Okay.
So, I mean, I'm just speculating here based on what you're saying, but that could be a potential implication because a lot of answers to changes in rainfall in the Caribbean have been attributed to remote Pacific SST changes.
Okay. So yeah, I think it's something to investigate. I guess one of the things to look at, since it's a global climate model, is to see within this model what the impacts are from the Eastern Pacific onto the precipitation over the Intra-Americas seas, and then compare that, I guess, to the local forcings that this would have on precipitation. So definitely something to look into. Thank you.
Great. Thanks, Vasu. We do have a few more questions. Let's take Nick's first. It could be a quick answer from you, Dion. How is the ocean model initialized?
This is the well, there was a spin-up run first with the low resolution the low resolution ocean coupled to the atmosphere, and after that we used that to once it's stable, we initialize that to the high resolution run, wait for it to be stable again, and then after that perform the runs. So it was a few steps to it.
Great.
Yeah.
Okay. And Ernesto, did you have a question? You're off mute.
Hi, Diane. Can you hear me?
Yes, I can.
So it's a kind of just a clarification, the first one. And you mentioned that you quantified or counted about 1,100 eddies. Is that correct?
Yeah. Well,
and how many years of simulation did you complete?
This is using 54 years.
And are these eddies just loop current warm core rings?
Yeah, they are anticyclonic eddies, so most of them are warm cores. Well, the way I identified them is using sea level anomalies. So they include both the loop currents and loop rings that would generate sea level anomalies. And they're all anticyclonic, so they will be warm.
So typically there's about one ring detached per year. So, I mean, we're talking that we would expect about 50 or so rings in that simulation. So what your number is telling me is that somehow, I mean, you either counted them separately by month or something like that. I mean, why is it 1,100 and not 50
rings?
Right.
Okay. So it's these are just identified. You're right. This is every month I count them because we have the monthly output, so that some of them are repeated. You're right, and in a sense, it's all a composite of that. So it's just identified. It's not that I track them and just consider one ring each year and one loop current. It was counting it every month, how many rings I can identify. And on average, every month I identify about two. One is the loop current itself, and then there's a loop ring that propagates out.
Okay, thank you.
Yeah, no problem.
Thanks, Ernesto. And we do have one final question. We'll take this one before we go to break. This is from Chunzai.
Okay.
He asked, you show warm eddies in your model run. And the first question, what about cold eddies? And the second question, what are the vertical structures in the ocean for these eddies?
Okay, those are very good questions. Cold eddies, we just started looking at it, so I haven't fully done the same composites for the cold eddies, but I have identified the cyclonic eddies, and they tend to be a lot less given the thresholds that I've used. I could definitely, once I've done the analysis, I can show what goes on with the cold eddies. In terms of the vertical structure of these eddies, they pretty much look like parabolic cone shape, bowls mostly underneath. So when we look at the isotherms, they're parabolic shape, like bowls. Yeah.
Great.
I don't know if that answers the question, but that's what I've seen.
Okay, thank you so much, Dion. Great presentation.
Thank you.
All righty. Thanks, everyone, for participating in our session today. This was session 5. We will break for exactly 1 hour, and we'll host a virtual poster session over this hour. Today's poster presenters are online over this next hour, and they're ready to answer your questions. So make sure you go to the website, check out their posters, scroll to the bottom, and you'll see a comment section that you can add questions and comments for them. We're going to begin promptly again at 3:30 p.m. Eastern Daylight Time. And if you'd like, you can leave your system on and connected during this hour break. We're going to keep everything set up and keep everyone on mute. Thanks, and see you all in an hour.
Thank you.